So let me remind you about computable categoricity. This is not widely known outside of computable structure theory, but it turns into a reasonable question, a question that should make sense here. So let's start with that. You have, once again, a computable field. So field where the domain is countable, you can list out the elements of the domain, you can do addition and multiplication, and therefore a number of other things. Okay, so categoricity in model theory is, let's see, is a property of a theory, right? A theory is omega categorical or some other cardinal if all models of the theory of that size are isomorphic. That's not what we're going for here. Computably categorical. I can write and talk at the same time. If here we're saying look at one particular isomorphism, I'm starting by saying one particular computable field, it's really a property of the isomorphism type of that field. And what we're saying is that for every other computable copy of that field, there is, okay, so we're assuming it's isomorphic. The question is it computably isomorphic? And computable categoricity says the answer should always be yes. Okay. So let's just do a really simple example to begin with. If I have my favorite computable copy of the real numbers, of the rational numbers, countable structure. And so I've listed out the rationals in some way and I can do my operations. And you have your favorite copy. And they don't have to be the same copy. I mean, we're allowed to think differently about these things, but we should be able to compute an isomorphism between them, right? I mean, so if I know how to do the addition, I guess maybe I need the multiplication too in this case, in your copy, I can just say, okay, in your copy, first of all, I'm going to figure out what element of your thing is 0. I'm going to just look for an x that adds to itself and equals itself. Find the 1, which will be a different element that multiplied by itself gives itself. And once I've got those, I'm off and running. I know how to do the addition and the multiplication in your structure, so I can say, oh, there's your 2, add again, there's your 3, your 4, your negative 1. If I know the multiplication, I can find 1 over n, 1 over negative n. And so I can then take my copy, where I know what these things are, basically, and pair each of my elements off of yours. Build an isomorphism. So this is saying something about being able to recognize elements in the structure, right? Rationals are easy. Other examples, well, so let's go to the other extreme, the algebraic closure of the, well, other extreme since we're talking algebraic fields in this course, the algebraic closure of the rationals. The way I've written it here, it looks like that's computably categorical. Think about that for a moment. You've just got some, so you're confronted with some kind of random but computable copy of Q bar. Or if you want to think of it this way, 2 copies and you have to build the isomorphism between them. Where do you start? So,
identify Q.
I had to start finding rationals, first thing, right? Okay, 0s and 1s, and you can certainly enumerate Q within each of these structures. And once you've got that, okay, so here's some arbitrary element of 1 copy of Q bar. You can add, you can multiply, you know that...
You find the minimal polynomial.
You know that this element is algebraic.
You find some element in the other field that has the same.
Okay.
And then you Yeah, and then you
So this turns out to satisfy some particular p of x that you know is irreducible because Q has a splitting algorithm.
And it doesn't matter which route you take because
Okay. And here you've got some choice where to map it, right? But if you know a root of this polynomial, you can map it to any root you want of that polynomial, and that will extend to an isomorphism between the two. Algebraically closed fields are nice this way, right? So that's safe. For the next element, just one catch there. You'd better find its minimal polynomial not just over Q, but over Q of the first element, right? But again, splitting algorithms do extend this way. We're not even using the fact that Q bar has a splitting algorithm here. We're using the fact that Q has a splitting algorithm because that's sort of where everything starts. And then that it extends to uniformly, so you can figure out what is the splitting algorithm for Q of A, you can find minimal polynomials, and you just do this forever, basically. A good model theorist would probably say, pick an element from this structure, map it here, and then next pick the next available element from this structure and figure out a pre-image for it, you know, back and forth. In the case of Q bar, you don't have to do this, because if you embed it into itself, the embedding has to be onto. Okay. If we were getting into transcendental fields, there might be some more issues that way, but we aren't. So today is really all going to be algebraic. Okay, so yeah, so Q bar is computably categorical.
I guess they're computably categorically quite a different way. I mean, I was
yeah.
When we needed computable stability in one paper. I mean, in the sense on the Q side, every isomorphism is computable.
Yeah.
There's
only one.
Whereas in Q bar, there's uncountably many, and obviously they are not generically computable. Computable isomorphisms.
Yeah, in Q, every single element is definable, right, by an existential formula, so you can do it effectively. And in Q bar, that's not true, but you've got enough wiggle room. You can get away with it somehow.
Sure, but I mean, I guess that means. Yeah, I mean, I was thinking about these phenomena where somehow you have the same field and we think about it in different ways, computably numbered, and then it can mean that I think a certain subset is decidable and you don't, because somehow the isomorphism. Yeah.
Right. Yeah. So this is one thing. I mean, if you wanted to prove that there's no computable isomorphism, maybe one way to do it would be to show that in this field a certain set is decidable, and over in the other field, the same set is not. Because if there's a computable isomorphism, then that can't happen, right? So a definable set here has to be mapped by any isomorphism to the set defined by the same formula over on the other side. So if there were some sort of difference in their decidability.
Sure, but I guess that's only really easy, that argument, if the set we start with is characteristic. I mean, is automorphism invariant, so you know what it will be mapped to on the other side, whereas otherwise you have the choice of what isomorphism do you want to pick.
I mean, there are times with computable categoricity where you can definitely do proofs like that. In the algebraic fields case, it's not quite as common.
Yeah. I guess this argument for Q bar also works for any Galois extension of Q.
Okay,
same argument.
Yeah. So the
finite or infinite. Yeah.
So if we didn't have Q bar, but we had something that was normal. Okay. Everybody remember? Students, I would expect I have to remind them that aren't here. But does everybody remember normality? Right. You know, if you got one root of an irreducible polynomial, you've got them all. That's really what we used for Q bar, right? Let me just mention here you remember the field that we came up with last time that had no splitting algorithm. Okay, so I started with the rationals and I joined square roots of those primes, piece of n, where n has appeared in the halting problem. Right? First of all, this was and is a computable field, right? Yeah, I mean, you just sort of, as numbers appear in the halting problem, you throw in their square roots and keep building the field as you go. Second of all, it did not have a splitting algorithm, because if it did, you could have told whether x squared minus pn has a square root. You could have decided the halting problem. It is normal, and it is computably categorical. Right? Got to think about that for a moment, maybe. But if somebody gives you an element of this field, so as always, you sort of start by finding the rationals, and then now one thing about finding the rationals, you kind of enumerate them rather than, you can decide whether a number is rational or not. Find its minimal polynomial over Q, and if it's x minus a, then it's rational. But if somebody just gives you a number and says, is this rational? You can't say, well, I've checked all the rationals and this is not one of them. Like, there's too many rationals. Apart from finding the minimal polynomial, that's the only way. But, okay, anyway, so as you're going through, listing out the rationals, sometimes you come to an element, and its minimal polynomial turns out to be x squared minus pn for some prime. And you say, oh, okay, first of all, I guess that means that n must be in the halting problem. Fine. Not really, relevant because that means this is in the field, that's all. Second of all, in the other copy of this field, there's got to be some similar element, and it's safe to map either of these square roots to either of those square roots, and the second one to the second one, maybe do that at the same time. And once you've done that, you can build from there, combination a plus b root pn and that sort of thing, that's all easy. So that's computably categorical. Is there anything that isn't? Okay, so let's just, without having written down a formal proof, of course, all normal computable algebraic fields. Okay.
Sure. I was thinking you can build, in exactly this way, you can build computable two copies of a computable field where one has a splitting algorithm and the other doesn't. I want to start with something like Q adjoin countably many transcendentals.
If we're going to do transcendentals here, okay, yes, that's possible.
Sure.
Was it coming? No, okay.
I guess we're looking for algebraic ones, right?
Yeah, my first reaction was, wait, we're talking algebraic fields. I don't think we've done this, but if you have two computable copies of the same algebraic field, either they both have a splitting algorithm or they both don't. Turns out that we haven't proven that. It's not too hard once you have Rabin's theorem.
Yeah. I guess we briefly talked about things of that kind last week.
Yeah, but that turns out to be a constant. The Turing degree of the splitting set is a constant.
Suppose you take something like, you start with Q, you join all the square roots of all the primes.
Sounds good.
And then you adjoin, and then you for each prime you adjoin either the square root or the square root of negative of the square of this.
Okay.
The square root of the square root of the square root or the square root of. Oh no, that doesn't.
I think it sounds like you're basically just adjoining the fourth root of Pn for every n, right? But
I don't want the.
That's not quite what you want, but let's think about it.
I want to do this, for n in the
halting problem or something like that.
Something like this.
So the first attempt was this, which is really just taking
I
know.
Oh, okay.
This is the first attempt. Didn't work.
Yeah.
Right.
No. That was not the.
So let's see. This is not normal, right? Does have a splitting algorithm. Yeah, it does have a splitting algorithm, but what I meant was it is computably categorical.
Wait, do you mean n in I mean, the first field ahead was not n and n, but n in the zero jump.
Right, okay,
And also,
that one won't
but
be...
also...
Yeah. Let's talk about this one first.
Okay,
Right? Just as an
okay.
example of something that's not normal, but does turn out to be computably categorical.
I mean, you only have one
Because
chance.
you know what's going on here. When you see a square root of a prime, you say, okay, let's be careful. There are two square roots of this prime. One of them has square roots of its own and the other doesn't. So let's go and figure out what, keep looking until we figure out which is which. Right, so that works perfectly well. The second step, which worked, is okay, now let's only put in some fourth roots of primes and not others. And let's put them in an undecidable way, computably enumerable, so that this field still can be a computable field. But now I see a square root of a prime. What should I do? Well, maybe it's a prime Pn, we can figure out the n. If I see that n go into the halting problem, then of course I should wait, then I know, okay, there's going to be a fourth root out there somewhere, and that will distinguish the two square roots of Pn. And so let me wait for that fourth root to appear, and when I see it in both fields, then I'll know which is which of the square roots is which. And the fourth roots themselves are not a problem. You can map them to the two fourth roots here either way. But if n has not yet gone into the halting problem, then I'm sitting there saying, what should I do? And to figure out what to do, you basically have to decide the halting problem. Right? Okay, so if anybody has come across the concept of computably inseparable sets, that ultimately would get used here to show, to give a proof that this is not computably categorical. The easiest way would be you can partition 0 prime into the disjoint union that says these are disjoint sets whose union is 0 prime. Disjoint union of two CE sets, which are, they're called computably inseparable. For all computable sets C and natural numbers, so it's not true that A is a subset of C and B is a subset of the complement. Okay, so if this happened, we would have called C a computable separation. Right? C is a set where, okay, I'm not telling you exactly what things are in A and what things are in B, but the things in A are all in C and the things in B are all outside of C, and C is computable, so there's sort of a way to distinguish A stuff from B stuff. There's just a certain amount of leftovers thrown in. If you had a computable, best way to say this. Okay, there are CE sets that are computably inseparable this way, and there's even a theorem that says every undecidable CE set can be partitioned into computably inseparable CE sets.
So do you require A and B to be CE?
Yeah, so
otherwise you could easily take ridiculous...
Yeah, okay, true. Yeah. I mean, the concept of computable inseparability applies to anything, but yeah, it's really easy to get if the sets are, it's much easier to get if the sets aren't CE. And I certainly do want them to be CE here. So, yeah. So, 0 prime and every other undecidable CE set can be partitioned into a pair of computably inseparable CE sets. And then the idea would be you build one copy of this field where you just put in sort of the fourth root of the first square root of Pn that you see. And you build another copy where when you see n go into 0 prime and you say, oh, I should add a fourth root, you say, okay, that n must be in either A or B. Enumerate A and B until it appears in one or the other. If it appeared in A, put in a fourth root of the first square root of Pn, put in a square root of the first square root of Pn. If it appeared in B, put in a square root of the other. And then an isomorphism between them would have given you a computable separation of these two sets. Even for the n's not in the halting problem, it would have made some sort of decision. And if n was in the halting problem, it would have decided specifically where to send the fourth root, and that would tell you, that would give you a separation of A and B. Okay. We can run through all of those details if somebody wants. This is probably not the best place to do it, so ask afterwards. Okay, so yeah, so there are...
How does this hang together with splitting algorithms?
So does this have a splitting algorithm?
I mean, no, I mean, you check whether x to the 4 minus pn has a root, and you can't.
Yeah, so yeah, does x to the 4th minus pn have a root, or does x squared minus the square root have a root? Either way, that's not decidable. Okay, so this has no splitting algorithm. Splitting algorithm would, I mean, if...
Sorry, what was the example? What shows that it's not a...
Okay, well, so I mean, the most basic version that Philip had was just look at the polynomials x to the 4th minus the nth prime.
You can't decide whether that is a root.
They have a root.
Oh, I see. Oh, you only have n in there. Okay.
Yeah, yeah. So now that...
Yeah.
Okay. All right, so this does not have a splitting algorithm. Let's see, even if you do, things can still go sort of wrong, however. So if I wanted to build this and have a splitting algorithm, I mean, I couldn't build this exact field, of course, but if I wanted to pull some sort of tricks like this and have a splitting algorithm, what I would need to do is I'd probably start off with all of that. And the square roots of Pn are sort of the ducks all lined up in a row. That if you want to build an isomorphism, you're going to have to map those square roots to the corresponding square roots in another field. I don't have to use square roots of the square roots as these tags. There are a lot of different polynomials I could use to tag one square root and not the other. Right? So coming up with them is a pain. I can refer you to a paper. I don't. More or less, you want to say work out some polynomial in two variables, some h of xy, such that, let's see, h of square root of Pn can have a root even while h of the other square root of Pn doesn't. And that's what was going on here, right? Okay. There are a lot of polynomials like that. And it's not all that hard to go in and work out some of them. It's a pain, and it's not something to spend time on here. But if I wanted to pull this sort of trick and have a splitting algorithm, then I start with all of this. I go through and once again start enumerating the halting problem. But, after a few steps, I'd say, okay, maybe the first number appears in the halting problem, let's say, so I put in a fourth root of that prime. Okay. And then I say, okay, enough of these x to the fourth minus Pn polynomials. I'm going to say now that all the one that I put in has a root, the rest of them don't. Okay, and I will stick to that for the rest of the construction of the computation of this field, the building of this field. But there are other polynomials out there that can serve the same purpose. So the next time a number goes into the halting problem, I use some other polynomial like this, maybe a different prime degree or something like that.
Right, but you have to somehow vary the h's in an uncomputable way to ensure that you can't do the same.
Well, so the argument about computable separations will still apply.
Yeah, that's fine. I mean, to ensure that this thing has a splitting algorithm so you can't pull the same trick, you need to, I guess you can do something like take a prime root of Pn where somehow the prime you consider grows uncomputably fast or something like this to ensure you can't.
Yeah, I don't think it's really as complicated as that. I mean, again, if we find a lot, for different primes, maybe, polynomials like this, and we simply use different prime degrees for each of them, so we're sort of saying that putting in a root of this one isn't going to mess with any of the others because we have extensions of different prime degrees.
Sure, but I mean, for this x to the 4 minus Pn argument, we just use that for the given Pn, we know what polynomial we need to check. So check whether n is
the first number that appeared in the halting problem.
Aha, okay, so you're numbering it not by the primes, but by how you enumerate the halting problem. Yeah, okay, I retract my objection. Yeah, that's going to be fine.
All right. So this is more of a construction. I won't go through it, but even with a splitting algorithm, you can run into trouble this way. Okay. So there's kind of a lot of chaos here at the moment. Let us try to bring some order out of it. So if we are given two computable algebraic fields, characteristic 0, let's say, to keep it simple, and we know they're isomorphic. The isomorphism tree is basically a situation of us looking at this and saying, okay, what are our options? So my trees grow upwards, so which is unfortunate right here, because I have to start down here. But okay. So let's see. So my tree is basically going to say, here I'm going to list out over here the elements of F, and on the right side I'll have the elements of E, and the question is, where should I map stuff? And just to get started, I'll find the 0 and the 1 in F, and I will map, I'm just going to write it with 1 here, but I'm certainly going to map 1 to 1. Then I come to the next element, let's just call it x0, whatever it is, in F. Well, I don't know what's a good idea, well, I know a lot of bad ideas. Right. So I can get rid of a lot of possibilities here. Find the minimal polynomial of x0 over q, and then start looking for roots of that polynomial in E. Okay. So if here I'm thinking of x as just being elements given by x, and let's say these. The y's represent elements of E here. I'm guaranteed sooner or later to find some whatever it is, y sub 26 or something, turns out to be a root of that minimal polynomial. Okay, this involves enumerating the rationals on both sides and using the splitting algorithm for the rationals. Possibly that's the only option. If it is, great, but how do I know that? And even if I do know it, it may not be. There may yet be, y sub 4,610 pops up, the root of that same minimal polynomial. Maybe there are more. Maybe. Only finitely many, certainly. Okay.
So the context is still that both of these are somehow algebraic over Q and
Yes.
abstractly isomorphic, I guess.
And we're assuming they are isomorphic to begin with. As you might have noticed in this process, you sort of fix an isomorphism type. You're allowed to assume whatever information is known is kind of computable about that type. If you knew it was Q bar, you could see it differently than if you were looking at Q or some of these others. But here I'm saying, okay, there's not a lot that we know. I'm not assuming a splitting algorithm. I'm not assuming much of anything except these are computable and algebraic. Okay. But I want to push on. So I'm building this tree, and it might take I never really know necessarily when I'm done enumerating this level. But I do want to keep going, so while that's happening, I'm going to push on and say, okay, where should the next thing here map? All right, okay, so find its minimal polynomial over the field Q of x0 within F. And say, okay, over on this side, if I plug in y26 in place of x0, let's look for roots of that. Also, if I plug in this y, 4610, in place of x0, let's look for roots of that in E. It's not guaranteed that I find any. For a particular, over y26, I mean, this might be like mapping the positive square root of Pn in there to the negative square root of Pn here. Maybe that was a bad idea. So it's not guaranteed that there's anything here or here, but there's got to be something somewhere because the fields are isomorphic. So, okay, so maybe that one dies off, and this finds three different possibilities. And again, you don't know if it's only three or if that's all, maybe there's another one still coming. But you keep going like that, and building this tree. Okay, do I need to draw anything more? I'm thinking
So each vertex of this tree corresponds to an embedding of the field Q adjoin x0 through xn into E.
Yes.
Is that right?
Yeah.
And
Each of them.
And each edge means that it extends. You're just and so
You've extended the previous.
So you're arguing that you can sort of computably. I mean, you can enumerate
the options.
You can enumerate the vertices and edges of the tree, but you might not know when you're done at
I might not know when I'm done, and I might not know if this is really a good idea.
Yeah, and then deciding whether they're computably enumerable means whether you can computably find.
Okay, so two things. First of all, an isomorphism would precisely be a path through this field. Right. Again, we didn't think about putting this map onto, but because they're algebraic fields, we can get away without doing it. Any embedding of an algebraic field into itself is automatically onto. Okay, and these are isomorphic, so that gives that to you. So every path here will be an isomorphism. First a homomorphism, then it's fields, and they're isomorphic, so an isomorphism. And every isomorphism corresponds to a path. Okay, so we've got a decent picture here of what's going on. Now the question is, well, you can ask several questions, but first, does this tree have a computable path? Computable path would be a computable isomorphism, right? It would tell you exactly where to send everything in F. Okay. So this brings us, this brings some order out of the chaos, but there's still a good question. When do trees like this have computable paths? Okay. The first thing what one should maybe do at this moment is, does anybody know the name Jean Buridan? 14th century French philosopher, remembered today mainly for his ass. Buridan's ass. Does anybody know the story? Buridan's ass was a donkey, an ass, who found himself in the happy position of being halfway between two delicious bales of hay, except that he was exactly halfway between them, and they looked equally scrumptious no matter how closely he examined. And so in the story, Buridan's ass could never decide whether to go this way or that way, and he wound up starving to death in the middle of the two bales of hay. Okay, so it is true. This is what everybody remembers Buridan for. I think historically it's not clear if this story was told by Buridan himself or by his critics, saying, oh, if you had a donkey who followed Buridan's views on free will and determinism and stuff, this is what would happen. Ridiculous, but okay, in the end of the story, everybody looks at the dead donkey and says, what an ass. Right. Okay. With that, Königslemma. Nice segue here. Let's... Okay, there are a few different things that are known as Königslemma. This one is sometimes called weak Königslemma, but in any case, every infinite finite branching tree has a path, and I'm not going to say this in general. For me, path always means an infinite path through the tree. So for the moment, trees are the same sort of thing as there. There's a root. Finite branching basically means finitely many nodes at every level, by induction. And infinite means infinitely many nodes, and I'm only talking about trees that go through finite levels. So the height of the tree could be omega, the natural numbers, but no trees of greater height than that. I mean, they exist, but I'm not worried about them here. Every infinite finite branching tree has an infinite path. Very easy proof. You start at the root. There are infinitely many nodes in this tree, but only finitely many nodes at level 1. So one of those has to have infinitely many above it. Okay, go to such a 1. There might be more than 1, of course, but okay, go to such a 1, and then do it again. There's only finitely many nodes here, but there's infinitely many nodes in total above, so one of those has infinite. So you build a path, right? Totally easy proof, except that I'm a computability theorist. I want to compute a path. And the natural thing to try to do is to say, okay, first of all, first problem I run into, okay, I'm looking at this tree, so how is the tree presented? Let's say nodes are just given as natural numbers, so that wasn't generality, 0 is the root. Somebody says, okay, here's node number 1, and here's node number 2, and this is number 3, and then they're just giving them in some kind of random way, sort of like over there, right? Nodes just appear, 5 and 6, and then later on at some stage, this appears. I'm guaranteed the tree is finite branching. The first problem would be, if I don't know if I can't compute the branching, then I'm pretty much sunk right away, right? Because, I could be looking at these 3 nodes and saying, okay, I've got to choose one of them, as far as I know. I make a choice, and then it turns out there was another node over here, and the only infinite path goes there. Okay, so for computability, usually we assume we can compute the branching function. Otherwise, the process of finding an infinite path seems pretty hopeless. I mean, there might still be a computable infinite path, in fact. The existence of one and coming up with one are sometimes different questions. But okay, anyway, so looking at this, so if I can compute the branching, then I say, okay, at level 1 there are exactly 3 nodes. And the natural thing to try is to say, well, maybe, you know, I can say, okay, how many successors does this have? And the function says just these 2. How many successors does this have? None at all. How many successors does this one have? 3. Okay, well, so 5 and 6, and I'll wait until eventually another one will appear. How many successors do these have? If I'm lucky, maybe at some point, I get to the spot where there are no successors anymore. And then I say, okay, that would have been a bad choice. So as long as I didn't make a choice yet, if I'm lucky, some of these nodes may eliminate themselves. Okay. Ideally, there would be only one node that has an infinite, that's on an infinite path. And if that's the case, then the others will all eliminate themselves. And if I just wait long enough, well, you know, all the rest will be gone, and I'll say, okay, this is the only option left, I'm taking it. The problem, of course, is if I do that, and it turns out that there were 2 nodes, if I wait, and it turns out that there were 2 nodes that were both on infinite paths, then I'm just sitting there forever, doing nothing. And both of those would have been good answers, and I never chose either one. And at the end of eternity, everybody looks at me and says, what an ass, right? So we computability theorists have some sympathy for Buridan's ass.
I have a question about that, because I was thinking this from the start of the lecture, but you could, instead of doing the automorphism group of Qs, the absolute Galois group, you could do the computable automorphism group. And what you are seeing here is somehow a representation of this computable automorphism. Just choose E equal to F. Don't choose the isomorphism, and you get all these kind of infinite paths going up.
Yeah. I think what you're getting here, I mean, if you do that sort of thing and E equals F and they're both Q bar, what you're getting, the paths are actually all the automorphisms, right? I mean, the computable paths are the computable automorphisms, and they're somewhere in there, but the paths are just all of them. That's what you were saying? Okay, yeah, okay. Yeah, so we're aiming for that next week. Yeah, that's where things are going here, although there's going to be a little detour tomorrow into something different that does play into it, but okay. But for now, if it's just a matter of, you know, does this tree have a computable path, sometimes the answer is no, right? Koenig's lemma is true, but it's not always effectively true. Okay.
I mean, if you have, oh, go ahead.
I mean, I guess this is just a remark. I mean, for this more from the logic point. I mean, I always find it helpful. I mean, things like Gödel's first incompleteness theorem or Russell's refinement tells you that you can't hope to find the decidable complete refinement of piano arithmetic, and you can somehow represent this as a tree property, because you need to decide whether you are allowed to throw in some sentence or not, and then at a given level of the tree you say, I haven't reached a contradiction in a million steps or whatnot, and that gives you a node, and that's a computable tree, because finding contradictions in finitely many steps is a computable thing, and if you were able to find a path, that would, a computable path, would be a decidable completion, but what Gödel and Hausdorff tell you can't.
Okay. Everybody happy with that, or was that new anywhere?
I mean, both, but.
Okay. You had a comment too.
Oh, maybe I'm getting ahead of where you want to be, but it seems that if you apply this to the context of your isomorphism, I mean, if you have a splitting algorithm, then you'll know how many vertices there are at each level. And so you can compute these branching. I guess that's branching function.
So
and also, if you have, I mean, if you know, if somebody tells you that there's a unique isomorphism between E and F, then by what you were saying, you can compute it, because you can just wait until at every level each branch will, all the bad branches will eventually die, and you can just wait until it happens before deciding where to go.
Okay, so the first point was having a splitting algorithm for the field F, not only for Q of course, but for the whole field F, allows you to compute the branching here. I mean, you could say, okay, how many roots does this particular polynomial irreducible over Q have in F? Bing, bing, bing. That computes the branching. And again, going up, that works. Second thing, if there is a unique path, so one thing you can say effectively, if there's only one path through the tree, then there is a single uniform procedure that lets you compute it. Which is, you know there's only one, so wait until every node except one at each level dies off. You know, do the ask thing. And it works if there's only one path.
That still requires the splitting algorithm?
Yes.
It seems like
I would have to sit and think, but I'm sure it does. Yeah, surely it does.
Okay.
Yeah. Just to piggyback on that, if there are only finitely many paths, then there's some level by which they've all separated, and you could, starting at the right node, you could sort of do the ask thing and compute the path from there along with the finite initial segment. So if there are only finitely many paths, then they are all computable, but there isn't necessarily a uniform way of finding them. You sort of have to know how far do I need to go, how many paths are there, and how far do I need to go to start, to have them all separate.
So what was the conclusion? That if somebody tells you how many there are, is that enough?
I mean, the most general statement, if there are only finitely many paths, then all of them are computable. But the procedure for finding them is different for different trees. It's not like finding a unique path where you just say, start at the bottom and I know what to do.
Okay, I see.
Right, okay.
I see.
Okay, but yeah, so even if there are only finitely many automorphisms of the field, we're thinking about that already, they will all be computable.
Can you imagine an interesting field where there isn't unique computable paths?
Well,
you have some things like Q that have no automorphisms and hence that, but what is an interesting example of something really unique, but unique?
Yeah, I have a feeling we could do that, but it would require, a priority argument and sort of messing with stuff a good deal. So let's not try right now, but...
What did you want?
Sorry, say that.
What did you want? You wanted a field such that what?
You're always talking about something in which we now hypothesize that there is a unique computable path in this corresponding tree.
Unique path.
Unique path. Yeah.
Wait, which do you? I mean, if there's one computable path and many other paths,
Yeah, sure.
I mean that is possible.
Just a unique path.
If it's a unique path, the path must be computable, and the field is rigid.
Yeah, right.
I mean,
so it's kind of,
yeah. Okay.
So then we agree. I can't imagine something easy, which is an example of this. Yeah.
Sure. I mean, as soon as you have automorphisms, I guess you must have several.
Yeah, sure. I was just trying to make sure we're not talking about the empty sets. Okay.
So, for example, the real algebraic numbers
Yeah.
is, I think that's an example. Yeah.
There's
The real algebraic numbers, that's a rigid field.
Yeah, sure.
And so Yeah, so any...
So you might start out saying, oh, several different cube roots of this polynomial. Yeah. I mean, it's a little bit irritating there because the automorphism would be the identity, and that's actually pretty easy to compute. But if you had two distinct copies of the real,
Yeah, that's what I mean. Yeah.
then it's a real question. Okay, which of these should I choose? Mm-hmm. Okay.
Yeah, then it is actually meant to be the way I thought it was. Yes, but it's,
Okay. I guess this may have been obvious, but to make the point, if we had F and yet another computable copy of it in place of E, the tree would be isomorphic, right? I mean, nodes might appear at different times or something, but you get the same tree. And in particular, if E were just F itself, you get the same tree. Okay. So let's see. What about this? Okay. So sometimes there's a computable isomorphism, but there doesn't have to be. How hard is it to compute a path? In one of these things, a computable finite branching tree where you can compute the branching function, and the tree is infinite, so there is a path. There doesn't have to be a computable path. Obvious first guess. If you have an oracle for the halting problem, could you compute a path? Let's just check. Okay, I mean, you think so. How?
Well, I mean, you check whether you're allowed to go to, I mean, you just do Koenig's argument. I mean, you want to check, am I allowed to choose one? And you need to check, will I die? I mean, will I eventually find a contradiction?
And I mean, the one thing, I mean, if trained computability theorists were here, they might say, wait, being infinite is pi02. Right? I mean, which is not wrong. But here, in the finite branching context, you're just saying,
a contradiction you will find at the
level
finite step.
that's empty. Yeah. So it's really just an existential question. Is it? I mean, let me say it in a positive way. Is it true that every level of the tree above this level contains a node above 1? And if that's true, then the tree above 1 is infinite. So by Koenig's lemma, there's a path. So it's safe to go that way. So with 0 prime. You could check whether 1 is on a path, you could check whether 3 is on a path, you could check whether 10 is on a path. One of them has to be, choose that one. Okay, do you really need 0 prime? You know the answer to that?
Well, low basis theory.
Aha, okay.
I know no computability theory, but this is my favorite theory.
Okay, yeah, good, okay. Let's see, it was Kreisel who first said 0 prime can do this, which is pretty obvious. And then I think Schoenfield proved there always is a path whose Turing degree is lower than 0 prime, strictly lower. And the culmination of that was, as Philip says, the low basis theorem. I forget the exact year, but this is Wafish and Soar, somewhere around 1970 or so, which says every infinite, and I'll put these all together, finite branching and computable branching. So computable, finite branching, computable tree, fine, has a path, let's call it P, okay, so this is the jump of P, the halting problem relative to P is only as hard as the halting problem itself. And so P is low. By definition. That's what low means. Your jump is only as hard as the halting problem. So there are low sets that are not computable, and if you believe this theorem and you believe that there doesn't have to be a computable path, that's a proof. But I mean, the existence of such sets, yeah, has been known since pretty far back in recursion theory, as it was then. But yeah, somewhat more recently, it turned out that trees like this always have paths that are a good deal simpler than the halting problem. Okay. And indeed, there are low Turing degrees, D, such that every such tree has a D computable. So, I mean, there are a lot of different trees like this, and you might say, oh, well, 1 degree, 1 low degree computes a path here, and another low degree computes a path over here. But there are single degrees that are low that compute paths through every such tree.
So suppose it's finite branching, but it's not completely finite branching.
Okay.
What happens to that?
Well, so basically then I would say the branching is a function. It has a Turing degree, at most 0 prime, because you know it's finite, so you just keep asking the halting problem, is there another node? And eventually it says no. Okay, so whatever the Turing degree of the branching function is, this same theorem works relative to that degree.
Oh, so instead of 0 prime, you'll have that thing.
You'll have the degree of the branching function. If it were fields, you would have the degree of the degree of the jump of the branching function. The jump of the path would be Turing equivalent to the jump of the branching function.
Oh, but the branch. Wait. Oh, but that branching function. Oh, so that I see. So that, but that it could be that could be 0 double jump.
Yeah. So
It's possible.
So you could make this as bad as 0 double jump.
But then okay. So but then P could still be. Yeah.
And then P in that case does not have to be computable from 0 jump, but it's pretty close. Its jump is 0 double jump.
Okay, so there are things below 0 jump whose jump is 0 double jump?
There are things just on either side of 0 jump that jump to 0 double jump. Yes.
Okay.
Yes. So, yeah. Okay. There's a name for these. You mentioned it already. I think you did. They're called PA degrees. Okay, they are. These are so down here we're not relativizing anymore. We're saying computable finite branching. PA degrees because these are precisely the degrees of complete extensions of Peano arithmetic. Okay, and in fact, so it's clear that if a degree computes a path through every tree like this, then do exactly what Philip was saying about make a tree where the paths are the complete extensions of PA, and a path through it will be a complete extension. So such a degree will compute, and in fact will be the degree of some complete extension of Peano arithmetic. And conversely, every degree of a complete extension of Peano arithmetic can do this, it turns out, can find a path.
I guess that's just because PA is one.
PA can do it.
Codes all computable things.
Yeah. So that's a class of some interest. And what that winds up saying here is, if you're looking at an isomorphism tree again, even if you have a splitting algorithm, it's 0 prime hard to say it's okay to map x0 to y26, or it's okay to map x0 to y4610. But there is an isomorphism which doesn't know how to compute 0 prime that still somehow can make a correct choice at every step. This is kind of weird. right? Again, 0 prime would let you say which nodes are good and which nodes are bad. The isomorphism, the path through the tree, can't do that. It just somehow knows a way to pick a good node at every level. And it couldn't tell you if the other one would have been a good choice or not, or the others would have been good choices or not.
How about if we don't demand that E and F are isomorphic a priori? I mean,
Okay. So if they're not isomorphic, this tree will turn out to be finite.
sure.
I
I mean, I guess
I don't know if that's as obvious as you seem to think it is, but
I mean, I guess I'm sort of asking how hard is the isomorphism problem for computable fields?
yeah, okay. So let's see. So if you have a splitting algorithm, then basically that says the answer is 0 prime. You just ask, does this tree ever have an every level? If you don't have a splitting algorithm, well, if you take the splitting set, SF, SF prime would tell you this, because SF will compute the branching.
Sure.
Right. Without the branching, that it's more of a problem. It's not 0 prime anymore. Yeah. So isomorphism problem there, and yeah, and one other fact about these PA degrees, there are 2 different degrees, PA degrees, such that the only degree below them is the degree of the computable sets. There is a so-called minimal pair of PA degrees, which means if you're dealing, so let's say you're dealing with a field F with a splitting algorithm, if it's not computably categorical, then there's no single degree that's the smallest degree which can compute the categoricity. There's no degree of categoricity in our language. As I recall, these fields were the first example of a structure where it was clear that there was no degree of categoricity that way. Very often it's 0 prime or 0 double or something like that.
Wait, what was the answer to
Okay, if the fields are not isomorphic.
question? Yeah, if the fields are not isomorphic, I mean, yeah, if you obviously you can compute if you have a 0 jump.
Right.
Splitting algorithm, yeah, you can.
Yeah, so it's sort of just Turing's lemma. It says if the fields are not isomorphic.
If you need a 0
okay.
jump, I mean, or is it possible, or is there going to be some low and it does that as well?
Yeah, so again, the first question is, can I compute the branching in the tree? So do I have splitting algorithm?
Yeah, let's just assume we have that.
So if we have that, then you're saying, well, is there a level where this tree is empty? Mm-hmm. And that's a 0 prime question.
Yeah.
And it is that hard for asking whether E and F are isomorphic. It is that hard. I mean, in general, it can be that hard.
Yeah, I mean, I guess I find it peculiar that somehow, testing whether they are isomorphic is kind of hard, but if they are isomorphic, then it's actually something easy to...
Easy isomorphic, almost computable isomorphism. Yeah.
Okay, so in general,
that's sort of what I'm going for today. There's this weirdness. Yeah.
Okay, so in general, it's that hard. Okay.
Yeah. So it's hard to determine whether the 2 trees are isomorphic. Alternatively, to determine whether x0 and y sub 42 or whatever, whether that map would extend to an isomorphism. Right, if E and F were equal, we'd say, are they in the same orbit under automorphisms? That's the natural way to ask that. And that, 0 prime if you have a splitting algorithm. It's at worst 0 prime. It can be 0 prime if you have a splitting algorithm. More generally, it's the jump of the splitting algorithm. So it could be 0 double at worst. So anything else I was thinking about here? I don't believe so. Yeah, that's... Okay, so this came out pretty well. It's 10 past 12, and I've covered what I wanted to do. More questions?
Yeah, I mean, sorry for belaboring this point. I still find this baffling that I mean, there are low PA degrees. I mean, in the sense that true arithmetic is fiendishly complicated, but somehow we still have some completions of PA that are
And
almost computable.
yeah, and you know, I mean, the first thing I would have said was sort of, well, okay, let's just talk about this briefly. Models of PA. Here's the standard model. Tenenbaum's theorem says the standard model is the only computable model of PA. People know this? I don't have a proof at my fingertips. We can look. I took a quick look last night, but it's not right there. So there are lots of non-standard models. And because there are these low completions of PA, there are models of PA, so that there's an effective version of the completeness theorem. And so there are non-standard models of PA where not just the atomic diagram, but the entire elementary diagram has this low degree. I mean, the standard model, okay, the atomic diagram is decidable, but you know, the existential diagram takes a jump. You know, deciding two quantifier things takes two jumps, and so on. There are these non-standard models where everything about every first-order fact about them can be decided from this degree that's low, that's almost computable. It's very weird. Non-standard models can be an interesting place to go when you're asking about decidability of existential theory and stuff like that, of course. You know, if you can't, if it's undecidable whether or not a certain polynomial has a solution, then that means that, well, if it's undecidable in general, if the first order theory in general is undecidable, then there are first order statements that are false, but cannot be refuted by PA. Let's see. So it's consistent with PA to say that they're true. So there's a non-standard model where they're true. So, you know, so thinking about non-standard models is hard because there aren't any computable ones. But on the other hand, they're so close, and you know, they would tell us a lot if we were able to get our hands on them.